Good morning. Today we're going to be working on finishing up section 2.5, limits at infinity. It's going to be kind of a big day, but that's okay. We're going to work through it together. So first of all, let's get to what we finished talking about last time, infinite limits at infinity. And it's possible for a limit to both be infinite, that is, our value L equals infinity, and for a limit at infinity, that is, x approaches infinity. We call this an infinite limit at infinity. And the definition goes something like this. If f of x becomes arbitrarily large as x becomes arbitrarily large, then we write the limit as x approaches infinity of f of x equals infinity. So let's start out again with this graph of the function f of x equals x cubed. We see that as x approaches positive infinity, our value of our function also approaches positive infinity. And as x approaches negative infinity, the value of our function also approaches negative infinity. So that's something that we're going to be looking at. And it's nice to know that infinite limits at infinity tell us about the behavior of polynomials for large magnitude values of x. So what exactly does that look like? That looks like these two graphs. So over here on the left-hand side, we've got the graph of x squared in black, a function we're all pretty familiar with, a graph of x to the power of 4 in red, one we're maybe not familiar with, but we know that it's a little bit steeper, and the graph of y equals x to the power of 6 in blue. And just like x to the fourth is steeper than x squared, x to the sixth is going to be steeper than x to the fourth. In these cases, as x approaches positive or negative infinity, our function approaches positive infinity. Now over here on the right, we have the graph of x cubed in black, x to the power of 5 in red, and x to the power of 7 in blue. And just like before, we see that x to the power of 5 is steeper than x to the power of 3, and x to the power of 7 is again steeper still. So this is sort of what we're talking about, and you'll see a lot of polynomials that behave like this. So again, we're coming back to this definition of what a polynomial is, and we can express a polynomial as p of x equals an times x to the power n plus a n minus 1 times x to the power a n minus 1 plus dot 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 everything in the middle plus a 1 times x to the power 1 plus a 0 times x to the power 0. And if you're interested in an just means that that's the real number coefficient associated with x to the power n, and an minus 1 is the real number coefficient associated with x to the power n minus 1. And these don't have to be any particular numbers, they can really be anything. So again, think about y equals mx plus b. Now, we can get creative with how we express these terms. And if we're interested in taking limits, maybe it's beneficial for us to be creative. So we can factor out an x to the power of n from each term. So we pull out x to the power n, and for our very first term, an times x to the power n, nothing happens. We just get left with a subscript n. In our second term, however, we've only got n minus 1 copies of x, which means we're going to have to divide by x in order to make sure that we end up with x. When we multiply everything back in, we end up with x to the power n minus 1. And we do that again with a n minus 2, x to the power n minus 2, and on and on and on again until we get to a0 divided by x to the power n. And in this way, it's easier to see that as we take the limit as x approaches plus and minus infinity, all of our terms but our first term go to 0. That is, we have something divided by x. As we take that to infinity, that goes to 0. Something divided by x squared, that goes to 0 as we take x towards infinity, and on and on and on again. We see that all of our terms except the first one go to 0. And in this way, p of x, as we're taking a limit towards infinity, is effectively just our very first coefficient, an, times x to the power n. And this is a pretty important concept for you to just understand. So maybe you need to watch this section of the video over again, maybe slow it down to half speed, something like that. But this is an important concept for you to understand, and it'll make the next few definitions make a lot more sense. So once you've gotten a hold on this, feel free to proceed. But we've got a few rules about infinite limits at infinity. And in the textbook, which I think we'll be getting a hold of pretty soon, this is theorem 2.6, and it's the first 3 entries in that theorem. So let n be a positive integer and p be the polynomial that we're talking about. And in this case, again, we have our original definition, p of x equals an times x to the power n plus an minus 1 times x to the power n minus 1 plus da 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 da, all that stuff in the middle that we don't want to rewrite, plus a0 times x to the power 0. And when this is our definition of the polynomial, the limit as x approaches positive or negative infinity of our function xn equals infinity when n is even. The limit as x approaches infinity of xn equals infinity, and the limit as x approaches negative infinity of xn equals negative infinity when n is odd. And the limit as x approaches plus or minus infinity of 1 over xn equals the limit as x approaches plus or minus infinity of x to the power negative n equals 0. So we saw this when we were looking at those graphs of x squared, x to the 4th, x to the 6th. 2, 4, and 6 are all even numbers, and they're the highest powers we see in our polynomial. So it makes sense that as we approach positive and negative infinity, our endpoints approach positive infinity on both sides. And then we saw in our graph of x cubed, x to the 5th, and x to the 7th, that on the right-hand side, we saw that x approaching infinity let x to the power n go to positive infinity, but on the left-hand side, we saw that as x approached negative infinity, our xn approached negative infinity. So let's go ahead and do some examples so that you guys can get familiar with working with these. So our very first example, we want to determine the following limits as x approaches positive and negative infinity. So our first function is p of x equals 3 times x to the 4th minus 6x squared plus x minus 10. We know that because this is a polynomial, it's fair for us to write that when we're taking the limit as x approaches positive or negative infinity of p of x, it's the same as taking the limit as x approaches positive and negative infinity of an x to the n. And in this case, our n is 4. We have 4 is our highest degree. So the coefficient that belongs to x to the power 4 is 3. So that's the limit as x approaches positive and negative infinity of 3 times x to the 4th. And we know because we've got this even power that these values are just going to equal infinity. Next, we're interested in what happens when we've maybe got a negative coefficient and x to an odd power. So in this case, we do the same thing as before, except this time we do have to break it up into positive infinity. So x approaches positive infinity of q of x is the same as the limit as x approaches positive infinity of negative 2 times x to the power 3. So because we've got this 3, we know that as it approaches positive infinity, the value is positive, so positive infinity, but we've also got this negative 2 term on the outside. So the magnitude's not very important, but the sign is important. We've got negative 2 times infinity, and that leads us to negative infinity. So let's go ahead and find the limit as x approaches negative infinity. And I'm going to skip that first step and automatically write negative 2 x to the power 3. Because we're approaching negative infinity this time, and we've got an odd power, we know that we're approaching negative infinity. But again, we've got that negative 2 out in front. So a negative times a negative equals a positive. We're approaching positive infinity. So the graph of this function looks something like this. And is this a precise graph? No, but this is about what it looks like, at least as far as the end behavior is concerned. So let's jump back into our slideshow here. So what we've been studying and what we've been talking about is the end behavior. And the behavior of polynomials as x approaches positive or negative infinity is an example of this end behavior. So what goes on at the very ends of these functions? What goes on at positive infinity or negative infinity? And now that we've covered polynomials, we can cover rational functions, so one polynomial divided by another polynomial, algebraic functions, so square roots, cube roots, roots of 1/4, stuff like that, and transcendental functions. You've maybe never heard the word transcendental before, but you've certainly worked with them. And these are going to be functions like e to the power of x, e to the power of negative x, the natural log of x, all that good stuff. And we're also going to be working with trigonometric functions. So your sine, cosine, tangent functions, and all of the ones that go along with it. So let's go ahead and start with some definitions. So suppose that f of x is defined as p of x divided by q of x, and it's a rational function, which means p of x is a polynomial, and we're going to use the subscript indices m for the coefficients and the powers, and q of x is also a polynomial, and we're going to use n as our subscripts for our coefficients b and our powers. And we assume that am and bn, the leading coefficients, are not equal to 0. Otherwise, this really wouldn't work. So in this case, the degree of p and q really matters. So is m or n greater or equal to one another? So if the degree of p of x is greater than the degree of q of x, then y equals 0 is a horizontal asymptote of f, and the limit as x approaches positive and negative infinity of f of x is equal to 0. So what does that mean? That looks like if I've got x squared divided by x, right? We know what that's going to look like. Or I've got some polynomial that the leading term is x to the 5 divided by a polynomial whose leading term is x to the 3rd. Next, we've got what if the degrees are equal? So what if I've got some x squared polynomial divided by another x squared polynomial? In that case, y equals our leading coefficients, am divided by bn, as a horizontal asymptote of f, and the limit as x approaches positive and negative infinity of f of x approach am divided by bn. Finally, we have the degree of p is less than q, and in this case, f has no horizontal asymptotes, and the limit as x approaches plus or minus infinity of f of x equals plus or minus infinity. It really depends on the degree that we just saw. And finally, we're interested in vertical asymptotes. So assuming f is as reduced as possible, vertical asymptotes occur at the zeros of q of x. So let's go ahead and look at an example. So in this example, we're interested in using limits at infinity to determine the end behavior of this rational function. And the function is f of x equals 3x plus 2 divided by x squared minus 1. So in this case, we're going to be a little bit sneaky. And we're going to do the same multiply by 1 trick that we've done in the past. So 3x plus 2 times 1. And in this case, I want my 1 to be 1 divided by x squared divided by 1 divided by x squared. And it's maybe not easy to see, but you can imagine that we've got one thing on top divided by itself. That's going to equal 1. So I'm more than welcome to do just that. So I've got 3x plus 2 times 1 over x squared divided by x squared minus 1 times 1 over x squared. We can distribute that in, and we get 3 divided by x plus 2 divided by x squared all over 1 minus 1 divided by x squared. And we're still interested in taking the limit of this function. So the limit as x approaches infinity of our function, just 3 over x plus 2 over x squared, quantity divided by 1 minus 1 over x squared. And in this case, our first term, our second term, and our fourth term all go to 0. So we're left with a 0 in the numerator divided by a 1 in the denominator, and all of that is going to equal 0. So just like we expected, the limit approaches 0. And you can check this in our notes that I just posted, where I said the degree of p of x is less than the degree of q of x, then we get a limit at 0. Back to our notes. So now that we've talked about the end behavior of rational functions, you can use that to figure out the end behavior of algebraic functions. So now let's talk about the end behavior of transcendental functions. Transcendental functions are things like e to the x, or you can pick 2 to the x, or 7 to the x, anything like that. So e to the x, e to the power of negative x, and the natural logarithm of x. Now remember, the natural logarithm differs from the regular logarithm because the regular logarithm is base 10, whereas the natural logarithm is base e. And e is a transcendental number, hence how they get the name. So the limit of x, the limit of e to the power of x as x approaches infinity is infinity, whereas the limit as e to the x as x approaches negative infinity is 0. So we can sketch those functions, and you'll see pictures of those later. The limit of e to the negative x as x approaches 0 is, or x approaches infinity is 0, and the limit of e to the negative x as x approaches negative infinity is positive infinity. So throwing that negative sign in our power really just flips which answer we're going to get. And then finally, we know that the natural logarithm of x can only accept values greater than 0, so we have to approach its end behavior from the right-hand side. So the limit of the natural log of x as x approaches 0 from the right-hand side is negative infinity. And the limit of natural log of x as x approaches infinity equals infinity. So let's go ahead and do some examples. So let's use our limits at infinity to determine the end behavior of the following functions. So the first one is f of x equals e to the 5x. And in this case, it might be saying, well, that doesn't look like what we typed in earlier on the PowerPoint. So what's going on here? Well, I'm going to call 5x just a variable t. And now we're interested in the limit as x approaches positive infinity of e to the t, and that looks exactly like what we were doing. Sorry, let me erase something really quick. The limit of e to the t as t approaches infinity. And we know this to be positive infinity. And we can do the same thing with the negative limit. So the limit as t approaches negative infinity of e to the t equals 0. That wasn't so hard, was it? So next we're interested in the limit of the function 4 minus the natural log of 3x. So limit as x goes to infinity of 4 minus the natural log of 3x. Again, we can just call t equals to 3x and take the limit as t approaches infinity of 4 minus the natural log of t. And in this case, we get positive infinity because this looks exactly like our definition. In the other case, the limit as t approaches 0 from the right of 4 minus natural log of t equals negative infinity. And you might be saying, Emily, why are you ignoring the 4? And to me, 4, it's always going to be the same. The limit of 4 as t approaches infinity is going to equal 4, but then we're subtracting positive infinity from that. That really doesn't do anything for us, right? We just get a number minus the biggest number you can imagine. Maybe it's a million, maybe it's a billion. We're talking infinity is like the amount of money that Jeff Bezos has. It's really, really crazy. It's the biggest number you could possibly imagine. And then it's even bigger than that. So the 4 doesn't really do anything for us. But we do need to be careful about what's going on with these negative signs. So 4 minus the natural log of t means we're going to switch the sign over here. Oh, draw, please. So the limit is actually equal to negative infinity in the first term and positive infinity in the second term because we're subtracting. We've got a minus sign that we need to account for. A negative times a negative is a positive, and a negative times a positive is a negative. Finally, let's deal with a trigonometric function. In this case, we're talking about cosine. And what's really going to help us here is not necessarily plugging in infinity, but drawing the graph of cosine. So I'm just going to do a quick sketch. So this is what the graph of cosine looks like. And we can see that it's periodic in nature. It's just going to repeat this pattern over and over and over again for as long as we let it go on. We can zoom out to look at 100 pi or 1,000 pi or even 1,000,000 pi, and we're still going to see the same oscillating pattern. And in this way, we know that, well, the function doesn't get squeezed to anything, and there's no value that it approaches when we're looking at infinity. So in this case, we say that the limit does not exist. The limit as x approaches positive or negative infinity of cosine of x does not exist. And that's going to be it for today.